What came before the Big Bang? It's the question everyone asks. The answer, nothing. There is no before. Time itself began. Space was born. And a man who couldn't move proved it all. This is Stephen Hawking's universe. This is your universe. Where time has a beginning, black holes evaporate and existence needs no creator. Let's begin. Welcome to Sleep Entangled. This is episode 3 of Through Their Eyes, Science's Greatest Minds, our series exploring profound science through the lives and journeys of history's most brilliant thinkers. Today, we enter the universe of Stephen Hawking, theoretical physicist, cosmologist, the voice of science for a generation, and perhaps the most famous scientist since Einstein. If you find wonder in these explorations, remember to subscribe and let curiosity guide your nights. Now settle in, breathe deeply, and prepare to see the universe as Hawking saw it. From the Big Bang to black holes, from the nature of time to the ultimate fate of everything. Stephen William Hawking was born on January 8, 1942 in Oxford, England, exactly 300 years after Galileo's death, a coincidence Hawking noted with amusement. His parents were both Oxford graduates at a time when university education was rare. His father, Frank, was a medical researcher. His mother, Isabel, one of the first female students admitted to Oxford, instilled in Stephen a love of learning and questioning. Young Stephen was bright but not exceptional. He was curious about how things worked, taking apart clocks and radios, building elaborate board games with friends. At school he was nicknamed Einstein, not as a compliment but mockingly, because he seemed awkward and his handwriting was terrible. Teachers thought he was intelligent but unfocused. He ranked in the middle of his class. In 1959, at age 17, Hawking entered Oxford University to study physics. He was bored. The coursework was too easy. He attended few lectures, calculated he worked about 1 hour per day, and still achieved a first-class degree. But he knew physics wasn't his strength. Mathematics was. So for graduate work he chose Cambridge, intending to study cosmology with Fred Hoyle, the famous astronomer. Hoyle wasn't available, so Hawking was assigned to Dennis Sciama instead. This turned out to be fortunate. Sciama was an excellent supervisor, encouraging, supportive, pushing Hawking to think deeply about the universe's largest questions. But something was wrong. During his final year at Oxford, Hawking had noticed he was becoming clumsy. He fell downstairs for no reason. His speech occasionally slurred. His hands wouldn't always do what he wanted. He ignored it. At Cambridge in 1963 it worsened. He went to doctors. The diagnosis: amyotrophic lateral sclerosis, ALS, also called motor neuron disease, a progressive degenerative condition attacking nerve cells controlling voluntary muscles. No cure, no treatment, steady, irreversible decline. The doctors gave him 2 years to live. He was 21 years old. Hawking fell into depression. Why work on a PhD if he'd be dead before finishing? Why do anything? He withdrew, spent time alone, drank too much, questioned everything. Then something changed. First, the disease progressed more slowly than predicted. He didn't die in 2 years. He was still alive, still thinking. Second, he fell in love. Jane Wilde, a languages student at Cambridge, saw past the diagnosis. They married in 1965. Jane gave him a reason to live, to work, to continue. Hawking decided if he was going to live a bit longer, he'd spend that time doing physics. Real physics. Deep questions about the universe's nature. He threw himself into work with intensity born from urgency. Every day might be his last. Make each one count. The disease progressed. By the 1970s, Hawking needed a wheelchair. By the 1980s, he could barely move. In 1985, pneumonia nearly killed him. A tracheotomy saved his life but took his voice. He'd communicated through slurred speech, increasingly difficult but still his own voice. Now, gone. A computer scientist created a speech synthesizer, a device with a cursor moving through words on a screen. Hawking selected words by twitching a muscle in his cheek. The machine spoke in a robotic American accent. This became Hawking's voice, famous worldwide, instantly recognizable. By the 1990s, Hawking could move only his eyes and one cheek muscle. By the 2000s, even that faded. His last years, he communicated through infrared sensors detecting tiny cheek twitches, one twitch to select letters, forming words at about 1 word per minute. Imagine that. Thinking at normal speed but communicating at 1 word per minute, forming complex cosmological arguments letter by letter, muscle twitch by muscle twitch, sentence by agonizing sentence. Yet Hawking continued. He worked, he wrote, he lectured, he appeared on television, met popes and presidents, became the public face of science. His most famous work came not in youth, but after diagnosis. The 1974 discovery that black holes emit radiation, now called Hawking radiation, came when he was already in a wheelchair, speech deteriorating. A Brief History of Time, published in 1988, sold more than 10 million copies, staying on bestseller lists for years. He wrote it while unable to move, using the speech synthesizer to dictate. Hawking lived 55 years beyond his 2-year prognosis. He died on March 14, 2018, Einstein's birthday, another coincidence he would have appreciated. He was 76. His life defied every prediction. His mind transcended his body's limitations, and through that mind we glimpsed the universe's deepest secrets, how it began, how it will end, and what lies beyond the edge of the known. This is Hawking's story. This is the universe he revealed. Let us begin where he began, with the question of origins. Chapter 1. The beginning. Did time have a start? Did the universe have a beginning? Did time itself start? Or has the cosmos existed forever, eternal and unchanging? For most of human history, creation myths provided answers. God spoke worlds into being. Cosmic eggs hatched. Titans shaped matter from chaos. But these were stories, not science. The question remained, did the universe begin? In the 1920s, observations changed everything. Edwin Hubble, using the world's largest telescope, discovered that distant galaxies are moving away from us. Not just a few, all of them. And the farther away a galaxy is, the faster it recedes. Space itself is expanding, carrying galaxies apart like dots on an inflating balloon. If space is expanding now, then in the past it was smaller. Run the expansion backward. Galaxies get closer, space contracts, density increases. Eventually you reach a moment when everything, all matter, all energy, all space, was compressed into an infinitesimally small point. This is the Big Bang. Not an explosion in space, but an expansion of space itself. Time and space emerged together from this initial singularity roughly 13.8 billion years ago. Before that moment, the question is meaningless. There is no before if time itself began. This troubled many people. If the universe had a beginning, what caused it? What came before? Where did the initial energy come from? These questions seem to demand a creator, a first cause, something outside the universe initiating existence. Hawking spent much of his career addressing these questions. His doctoral thesis, completed in 1966 while struggling with worsening ALS, examined the universe's singularities, points where physics breaks down. He proved, along with mathematician Roger Penrose, that general relativity predicts singularities are inevitable if the universe is expanding and contains matter. This was called the singularity theorem. It showed that Einstein's equations, applied to an expanding universe, inevitably lead back to a singular beginning, a point where density and curvature become infinite, where physics as we know it ceases to function. But Hawking wasn't satisfied. Singularities are where theories break down. At infinite density, general relativity gives nonsensical answers. Quantum mechanics must become important. But general relativity and quantum mechanics are incompatible. They give different, contradictory predictions at very small scales and high energies. So Hawking began working on quantum cosmology, applying quantum mechanics to the entire universe. What happens to the Big Bang singularity when you include quantum effects? Does it change the picture? Can quantum mechanics avoid the singularity, provide a more complete description of the universe's origin? In 1983, Hawking and James Hartley proposed the no-boundary proposal. It's a radical idea. The universe has no beginning, not in the sense that it's eternal, but in a subtler sense. Time near the Big Bang behaves differently than it does now. As you approach the moment we call the beginning, time gradually becomes more space-like. The distinction between time and space blurs. The universe's history, traced backward, smoothly transitions from expanding time into a closed spatial geometry with no edge, no boundary, no singularity. Imagine Earth's surface. You can travel south toward the South Pole. As you approach, you're moving toward what seems like an endpoint, the pole itself. But when you reach it, there's no edge. You've arrived at a point, yes, but you can turn around and go north. The surface is finite, yet has no boundary. Space curves back on itself. Hawking proposed the universe's history is similar. Time near the Big Bang curves becomes space-like, and the universe smoothly emerges from quantum geometry with no singular beginning, no moment of creation, no before. Oh, in Hawking's words, the universe would be completely self-contained and not affected by anything outside itself. It would neither be created nor destroyed. It would just be. This is philosophically profound. If the universe has no boundary in time, no beginning requiring a cause, then existence becomes a brute fact, a self-contained reality requiring no external explanation. God becomes unnecessary, at least as a first cause. Hawking was not particularly religious. He once said, "Before we understand science, it is natural to believe that God created the universe, but now science offers a more convincing explanation." He didn't deny spirituality's value, but saw no need for supernatural intervention in cosmology. The laws of physics, applied consistently, explain the universe's existence. This view troubles some and liberates others. If the universe created itself through quantum processes, then we live in a cosmos governed entirely by natural law, comprehensible through reason and mathematics. No miracles needed, no special creation, just physics. But Hawking acknowledged uncertainty. The no-boundary proposal is speculative. We lack a complete theory of quantum gravity. String theory, loop quantum gravity, and other approaches might modify the picture. Observations cannot directly test what happened at the universe's origin. It's beyond observational reach, hidden behind horizons of time and energy. Yet progress is possible. The cosmic microwave background, radiation from 380,000 years after the Big Bang, carries imprints of earlier conditions. Fluctuations in this radiation match predictions from inflationary cosmology, supporting the idea that the universe underwent rapid expansion in its first fraction of a second. Gravitational waves from the Big Bang might be detectable, offering another window into the earliest moments. Hawking's work transformed cosmology from philosophical speculation into mathematical physics. His singularity theorem showed general relativity predicts a beginning. His quantum cosmology suggested that beginning might not be a singular moment, but a smooth quantum emergence. Both ideas have shaped decades of research. So did the universe have a beginning? In classical general relativity, yes. A singularity 13.8 billion years ago from which everything emerged. In quantum cosmology, maybe not. Time itself might emerge smoothly from quantum geometry, with no boundary, no first moment. The question remains open, but Hawking gave us the tools to ask it precisely. And he did all this while losing the ability to walk, to speak, to move. His body deteriorated, but his mind never wavered. He thought deeply about origins while confronting his own mortality. He asked, where did the universe come from? How did it begin? And he found answers, partial, tentative, but mathematically rigorous, that reshaped our understanding of existence itself. So as you rest, as you drift into contemplation, consider, you exist in a universe that may have begun or may be beginningless. Time itself might have started, or it might smoothly emerge from quantum geometry. Either way, the cosmos you inhabit is comprehensible, governed by laws we can discover, shaped by processes we can model. Hawking showed us this. Now let us explore what he learned about the universe's large-scale structure and evolution. Chapter 2. Cosmic expansion. The universe grows. The universe is not static. It moves, expands, evolves. Every galaxy rushes away from every other galaxy, carried by space itself stretching like fabric pulled tight. This expansion is not galaxies flying through space, but space itself growing, creating distance where none existed before. Edwin Hubble discovered this in 1929. By measuring light from distant galaxies, he found a pattern. The farther away a galaxy, the faster it recedes. This relationship, now called Hubble's law, revealed that space expands uniformly. Double the distance, double the recession speed. Triple the distance, triple the speed. The entire cosmos participates in a grand, coordinated expansion. But expansion raises questions. If the universe is expanding, what drives it? What determines the expansion rate? Will it expand forever, or eventually collapse? And most intriguingly, has expansion always been smooth, or did something dramatic happen early in cosmic history? Stephen Hawking worked on these questions throughout the 1970s and 1980s, often collaborating with other cosmologists while his body steadily failed. By this time, he was in a wheelchair, his speech slurred but still comprehensible. He couldn't write equations on a blackboard. Instead, he visualized them mentally, manipulating complex mathematical structures entirely in his mind, then dictated results to colleagues. This method, pure thought, no notation, forced him to develop geometric intuition. While others calculated with symbols, Hawking pictured space-time itself, curved surfaces, singularities, horizons. This visualization became his strength. He saw relationships others missed because he thought in shapes rather than symbols. One of the universe's great mysteries involves its early moments. If you run expansion backward, the universe becomes denser and hotter. At 1 second after the Big Bang, temperatures exceeded 10 billion degrees. hot enough to fuse hydrogen into helium. At 1 millisecond, quarks and gluons, the building blocks of protons and neutrons, swam freely in a plasma soup. Earlier still, energy so high that physics becomes uncertain. But there's a problem. The universe is remarkably uniform. Look in any direction. Galaxies are distributed similarly. The cosmic microwave background, radiation from 380,000 years after the Big Bang, has nearly identical temperature everywhere, 2.725 Kelvin, varying by only 1 part in 100,000. Why is this surprising? Because regions of space on opposite sides of the observable universe, separated by billions of light years, could never have communicated. Light from one region hasn't had time to reach the other since the Big Bang. They're causally disconnected. No signal, no influence could have passed between them. Yet they have the same temperature, the same properties, the same structure. How did causally disconnected regions become so similar? It's like finding two people on opposite sides of Earth wearing identical custom-made suits, yet they've never met, never communicated, have no common tailor. The coincidence seems impossible. In 1980, physicist Alan Guth proposed a solution: cosmic inflation. He suggested that in the universe's first fraction of a second, specifically around 10 to the power of minus 36 seconds after the Big Bang, space underwent exponential expansion. Not gradual growth, but explosive inflation, doubling in size every tiny instant. In less than a microsecond, a region smaller than an atom expanded to the size of a grapefruit, then kept going. This sounds wild, but it solves problems. Before inflation, the entire observable universe was compressed into a tiny region, small enough that all parts could communicate, reach thermal equilibrium, become uniform. Then inflation stretched this tiny uniform region into something vastly larger. The uniformity we see today is the stretched remnant of an originally small, well-mixed patch. Hawking contributed to inflation's mathematical formulation. He worked with cosmologist James Hartle and others to understand quantum fluctuations during inflation, tiny random variations in energy density that got stretched to cosmic scales. These fluctuations became the seeds of structure. Slightly denser regions attracted more matter, eventually forming galaxies, stars, planets. The cosmic microwave background's tiny temperature variations, those 1 part in 100,000 differences, match predictions from quantum fluctuations during inflation. This is remarkable. The larger structures in the universe, superclusters of galaxies, cosmic filaments, voids, originated from quantum uncertainty in the first instant of time. The quantum and cosmic connect directly. Hawking's work also addressed what drives expansion. In 1998, observations shocked cosmologists. Astronomers measuring distant supernovae, exploding stars that serve as cosmic distance markers, discovered something unexpected. The universe's expansion is accelerating. Galaxies aren't just moving apart, they're moving apart faster over time. This contradicted expectations. Gravity should slow expansion. Galaxies pull on each other, creating an attractive force that decelerates cosmic growth. Yet expansion accelerates. Something must be pushing galaxies apart, counteracting gravity. We call this mysterious force dark energy. It constitutes roughly 68% of the universe's energy content. We don't know what it is. It might be a property of space itself, a cosmological constant, as Einstein once proposed. It might be a dynamic field permeating the cosmos, or it might indicate our understanding of gravity is incomplete. We simply don't know. Hawking speculated about dark energy's implications. If expansion accelerates forever, galaxies will eventually recede faster than light can travel between them. Future civilizations will see fewer and fewer galaxies as distant ones cross beyond observable horizons. Eventually, each galaxy becomes an island universe, alone in expanding space, surrounded by darkness. This is the universe's far future. Cold, dark, isolated. Stars burn out. Black holes evaporate. Expansion continues, pulling everything apart until even atoms might tear asunder in a scenario called the Big Rip. Or perhaps dark energy stabilizes, and the universe expands eternally into increasing cold and emptiness, a heat death, where no energy gradients remain, no work can be done, no complexity survives. Hawking found these scenarios fascinating rather than depressing. The universe's fate depends on physics we're still uncovering. Dark energy's nature will determine cosmic destiny, and that nature is discoverable. Observations, experiments, theory. These tools let us probe the universe's ultimate fate. By the mid-1980s, Hawking could no longer speak clearly. His voice had deteriorated to a slurred whisper understood only by close colleagues and family. He used a speech synthesizer occasionally but resisted full dependence on it. He still wanted his own voice, even if barely functional. Yet his scientific output remained extraordinary. Papers, lectures, collaborations, he continued working despite physical limitations. Colleagues marveled at his ability to manipulate complex equations mentally, to see through mathematical fog to physical truth. His geometric intuition, honed by necessity, became legendary. The universe expands. It grew from quantum seeds, inflated exponentially, now accelerates into an uncertain future. And we understand this because people like Hawking refused to accept ignorance, insisted on asking questions, pursued answers with rigor and creativity. So as you settle, as your mind drifts toward rest, imagine you exist in an expanding cosmos, carried through space on a galaxy, rushing outward with countless others, all participants in a cosmic dance that began 13.8 billion years ago and continues tonight while you sleep. The universe grows, time flows, and we are here, briefly, to witness and understand. Now let us turn to the universe's strangest objects, the places where space and time break down entirely. Chapter 3. Black holes, where space-time breaks. Black holes are regions where gravity becomes so intense that nothing, not light, not matter, not information, can escape. They are the universe's ultimate prisons, points of no return, places where the fabric of space-time tears and physics as we know it fails. Einstein's general relativity predicts black holes. His equations describe how mass warps space-time, creating gravity. Place enough mass in a small enough region, and space-time curves so severely that it closes in on itself. A boundary forms, the event horizon, beyond which escape becomes impossible. Anything crossing this horizon is lost forever, doomed to fall toward the central singularity where density becomes infinite and physics breaks down. For decades, physicists debated whether black holes actually exist or are merely mathematical curiosities. Einstein himself doubted them. The idea seemed too extreme, objects so dense that space itself becomes a trap. Surely nature avoids such extremes, but observations proved otherwise. In the 1960s and 1970s, astronomers found evidence. X-ray sources in binary star systems where an invisible companion pulled matter from a visible star. The infalling matter heated up, emitting X-rays before disappearing. The invisible companion was too massive to be a neutron star. It had to be a black hole. Then came Cygnus X1, a binary system 6,000 light-years away. Astronomers measured the invisible object's mass, more than 15 times the Sun's mass, compressed into a region smaller than a city. Nothing else fits the data. Cygnus X1 contains a black hole. Stephen Hawking famously made a bet with physicist Kip Thorne in 1974. Hawking bet against black holes. He argued Cygnus X1 might be something else. Thorne bet that it was indeed a black hole. This seems strange. Hawking had proven theorems about black holes, worked extensively on their properties. Why bet against them? He explained later. It was insurance. If black holes don't exist, at least he'd win the bet and get a subscription to a magazine. If they do exist, his life's work would be validated. Either way, something positive. This wry humour characterised Hawking throughout his life, finding levity in cosmic mysteries and personal challenges alike. He lost the bet. Cygnus X1 is a black hole. In 1990, Hawking conceded, giving Thorne a subscription to Penthouse magazine, as originally wagered. Thorne, slightly embarrassed, accepted. By then, Hawking had spent 2 decades thinking about black holes more deeply than almost anyone. His doctoral work with Roger Penrose proved singularity theorems, mathematical demonstrations that singularities are inevitable in gravitational collapse. When a massive star exhausts its fuel and collapses, if its mass exceeds a certain threshold, nothing stops the collapse. It shrinks to a point, forming a singularity surrounded by an event horizon. A black hole is born. Hawking calculated black hole properties. He showed that black holes have just 3 characteristics: mass, charge, and spin. Nothing else. It doesn't matter what fell in: a star, a planet, a library's worth of books. Once inside the horizon, all information about the infalling matter is lost. The black hole remembers only total mass, total charge, total angular momentum. This is called the no-hair theorem. Black holes have no hair, meaning no distinguishing features beyond those 3 numbers. This simplicity is shocking. You could throw in a complex object, say a computer containing all human knowledge, and the black hole gains mass but reveals nothing about what fell in. All that information seems destroyed, erased from the universe. This worried physicists. Quantum mechanics says information is conserved. It can't be destroyed, only transformed. But black holes appear to destroy information permanently. Hawking would spend decades wrestling with this paradox, but first he made his most famous discovery, one that revolutionized our understanding of black holes and revealed them not as eternal prisons, but as slowly evaporating objects with a temperature, an entropy, and a finite lifetime. The universe contains black holes ranging from stellar mass, formed when massive stars collapse, to supermassive giants at galaxy centers, millions or billions of times the Sun's mass. Our galaxy's center hosts Sagittarius A star, a black hole of about 4 million solar masses. When matter swirls into it, friction heats the infalling gas to millions of degrees, creating brilliant radiation detectable across the electromagnetic spectrum. In 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow. The dark silhouette cast against glowing infalling matter surrounding the supermassive black hole at the center of galaxy M87. The image matched predictions from general relativity with stunning precision. Black holes exist. They are real, and they behave exactly as Einstein's century-old equations predict. Hawking never directly observed a black hole. His work was theoretical, but his insights transformed how we think about them. Before Hawking, black holes were seen as simple. Matter falls in, nothing comes out. The end. After Hawking, They became thermodynamic objects with temperature, entropy, and radiation. Participants in the universe's energy exchanges, not isolated exceptions to physical law. By the early 1970s, when Hawking began his deepest work on black holes, his condition had worsened significantly. He needed help with basic tasks. His speech was difficult for strangers to understand, yet his mind remained sharp, focused, relentlessly curious. He once described his approach to physics: visualize the geometry, see space-time as a curved surface, imagine how particles move through that curvature. This mental visualization compensated for his inability to write equations. His students and colleagues would present problems Hawking would think, sometimes for days, then announce results. Often the results were correct, derived through pure geometric intuition, without intermediate algebraic steps. This method led him to black hole thermodynamics. He thought about event horizons geometrically, about particles near the horizon, about quantum fields in curved space-time, and he realized something astonishing. Black holes are not perfectly black. They glow, they radiate, they evaporate. So as you rest, as you contemplate the darkness behind closed eyes, imagine, scattered through the cosmos are regions where light itself cannot escape, where space-time curves so severely that nothing returns. Yet even these ultimate prisons are not eternal. They leak, they glow, they slowly, steadily give back what they have taken. Hawking showed us this. Now, let us see how. Chapter 4. Hawking Radiation. Black Holes Evaporate. In 1974, Stephen Hawking made a discovery that shocked the physics community. He proved that black holes are not completely black. They emit radiation, they have a temperature, and over immense timescales they evaporate completely, vanishing in a final burst of energy. This was revolutionary. Black holes, by definition, trap everything. The event horizon is a one-way boundary. Cross it, and you can never return. How can something that traps light also emit radiation? The answer lies in quantum mechanics, specifically in the strange behavior of empty space. According to quantum field theory, what we call the vacuum, empty space, is not truly empty. It seethes with quantum activity. Virtual particle pairs constantly pop into existence. A particle and its antiparticle appear together, exist briefly, then annihilate, returning their energy to the vacuum. This happens everywhere, all the time, at scales too small and timescales too brief to observe directly. Near a black hole's event horizon, something remarkable happens to these virtual pairs. Normally they appear and annihilate almost instantly. But at the horizon, space is so severely curved that sometimes the pair separates before annihilating. One particle falls into the black hole, the other escapes to infinity. The escaping particle becomes real. It carries energy away from the black hole. To conserve energy, the infalling particle must have negative energy relative to the black hole. This reduces the black hole's mass slightly. The black hole loses energy. It evaporates. This process, now called Hawking radiation, means black holes glow with thermal radiation, like a hot object radiating heat. The temperature depends on mass. Smaller black holes are hotter. A stellar mass black hole has a temperature of about 1/10,000,000th of a Kelvin, far colder than the cosmic microwave background. It absorbs more radiation than it emits, growing rather than shrinking. But a tiny black hole, say one with the mass of a mountain, would be much hotter, perhaps millions of degrees. It would radiate furiously, losing mass rapidly, becoming hotter as it shrinks. Smaller mass means higher temperature. accelerating its evaporation until finally exploding in a burst of high-energy particles and radiation. Hawking calculated this in 1974. He was in a wheelchair, speech deteriorating, working with graduate students and collaborators to develop the mathematics. The calculation required combining general relativity, which describes curved space-time near black holes, with quantum field theory, which describes particle creation and annihilation. These two theories don't normally work together. They conflict at small scales and high energies, but near a black hole horizon, both are essential. Hawking found a way to merge them, at least approximately. He treated the space-time background classically, using general relativity, but analysed quantum fields propagating through that curved background. This semi-classical approach isn't perfect. A full theory of quantum gravity would be better, but it was good enough to reveal Hawking radiation. When he first presented the result at a conference, many physicists were skeptical. Black holes emit radiation, they have temperature. This contradicted the Noether theorem's implication that black holes are featureless inert objects. How can something with temperature be featureless? The answer: black hole thermodynamics. Jacob Bekenstein had earlier proposed that black holes have entropy, a measure of disorder or information content. Bekenstein suggested entropy is proportional to the event horizon's surface area. More area means more entropy. This seemed strange. Thermodynamic entropy usually relates to volume. More volume means more ways to arrange particles, thus more entropy. But for black holes, it's area. Hawking's radiation provided the missing piece. Temperature and entropy are related thermodynamically. If black holes have temperature from Hawking radiation, they must have entropy, as Bekenstein proposed. The laws of thermodynamics apply to black holes just as they apply to steam engines or stars. Black holes are thermodynamic systems. This revelation unified disparate ideas: gravity, general relativity, quantum mechanics, particle creation, and thermodynamics, heat, entropy. It suggested that information, energy, and space-time geometry are deeply connected, that the universe's fundamental laws interweave in ways we're still understanding. But Hawking radiation created a paradox, one that would haunt Hawking for decades and remains unresolved today. If a black hole evaporates completely, where does the information go? Imagine throwing a book into a black hole. The book contains information, its text, structure, the arrangement of atoms. When it crosses the horizon, that information seems lost, hidden behind the event horizon where we cannot access it. Fine so far, the information is inside the black hole, but now the black hole evaporates via Hawking radiation. Eventually it disappears entirely. The radiation emitted, Hawking showed, is thermal, random, containing no information about what fell in. It's like heat radiating from a fire. The fire destroys a book. The heat carries no trace of the book's text. So the information that went into the black hole seems destroyed when the black hole evaporates. But quantum mechanics forbids information destruction. It's a fundamental principle. Information is conserved. If you know a system's initial state and the laws governing its evolution, you can in principle determine its future and past states. Information cannot simply vanish. Yet Hawking's calculations suggested it does. This is the black hole information paradox. It's one of theoretical physics' deepest puzzles, pointing to a conflict between quantum mechanics and general relativity that we don't yet know how to resolve. Hawking initially believed information is destroyed, that black hole evaporation represents an exception to quantum mechanics rules. Most physicists disagreed. This led to debates, bets, arguments spanning decades. In 2004, Hawking reversed his position. He presented calculations suggesting information might escape after all, encoded somehow in the Hawking radiation's subtle correlations. He conceded a bet with physicist John Priskill, giving him an encyclopedia. So information can be retrieved, Hawking joked, but the paradox remains unsolved. How exactly does information escape? Through what mechanism? Does it come out gradually during evaporation, or all at once in the final explosion? Does the horizon act as a hologram, encoding interior information on its surface? These questions drive current research in quantum gravity, string theory, and black hole thermodynamics. Hawking's 1974 discovery of black hole radiation stands as one of theoretical physics' great achievements. It revealed that gravity, quantum mechanics, and thermodynamics are unified at a deep level. It showed that black holes are not eternal but have lifetimes. It created paradoxes that push us toward a more complete theory of quantum gravity, and Hawking did this while his body failed. By 1974, he required constant assistance. His children were young: Robert, born in 1967, Lucy in 1970, Timothy in 1979. His wife Jane managed household, childcare, and Stephen's increasing needs. Colleagues helped with research, translating his slurred speech, writing down ideas he communicated through immense effort. Yet he persisted. He visualized curved space-time, quantum fields, particle creation at horizons. He saw what others missed, and he shared it, transforming our understanding of the universe's strangest objects. So as your thoughts drift towards sleep, consider: every black hole in the cosmos glows faintly with Hawking radiation, slowly returning to the universe what it has consumed. These ultimate prisons have finite sentences. Even the darkest objects shine if you look closely enough. Now let us ask, what is time itself, and why does it flow in one direction? Chapter 5. Time's arrow. Why does time flow? Time flows forward. We remember the past but not the future. We grow older, never younger. Eggs break, never unbreak. Entropy increases, never decreases. The universe marches toward greater disorder, irreversibly, inexorably. But why? The fundamental laws of physics are time-symmetric. Newton's laws, Maxwell's equations, Einstein's relativity, even quantum mechanics, all these work equally well forward or backward in time. If you filmed particles colliding and played the video in reverse, the reversed motion would obey the same physical laws. Time's direction doesn't appear in the equations, yet our experience violates this symmetry. We perceive a clear arrow of time pointing from past to future. The universe's history seems directional. Stars form, burn, die. Complexity emerges, then dissipates. Life evolves, then goes extinct. Time has a direction, even though fundamental laws don't prefer one direction over another. This puzzle fascinated Stephen Hawking. Why does time flow forward? Is the arrow of time fundamental, or does it emerge from something deeper? And most intriguingly, is time's arrow connected to the universe's expansion, its origins, its ultimate fate? There are actually several arrows of time pointing in the same direction, but arising from different phenomena. The thermodynamic arrow is the most familiar. Entropy increases over time. The second law of thermodynamics states that in a closed system, disorder always grows. A broken egg doesn't spontaneously reassemble because the assembled state is highly ordered, while the broken state is disordered. Systems evolve toward disorder, but why? The answer involves statistics. There are vastly more disordered arrangements of molecules than ordered ones. A trillion ways to arrange broken eggshell fragments, but only one way to arrange them into an intact egg. Random processes naturally explore the vastly more numerous disordered states. It's not that disorder is preferred, it's just statistically overwhelming. Yet this raises a deeper question. Why was entropy low in the past? If the universe evolves toward disorder, then tracing time backward, we reach increasingly ordered states. At the Big Bang, entropy was extremely low. The universe was in a highly special, non-generic state. Why? Why did the universe begin ordered rather than disordered? Hawking worked on this puzzle, connecting it to cosmology. One possibility: the universe's smooth, uniform initial conditions, as suggested by cosmic inflation, correspond to low entropy. Inflation stretched space smooth, eliminating wrinkles and irregularities. This smoothness is a low entropy state. As the universe evolves, gravity causes matter to clump, forming stars, galaxies, black holes, higher entropy configurations. The thermodynamic arrow emerges from cosmological initial conditions, but there's more. We also have a psychological arrow of time. We remember the past, not the future. This seems connected to thermodynamics. Memory formation increases entropy. You must record information, create physical changes in your brain. Recording past events requires thermodynamically irreversible processes, so our psychological sense of time's direction may be a consequence of the thermodynamic arrow. There's also a cosmological arrow. The universe expands, space grows over time, run time backward, and space contracts. This arrow seems fundamental. It's tied to the universe's dynamics, the expansion driven by the Big Bang. Hawking asked, are these arrows connected? Must they all point the same direction? What would happen if the universe's expansion reversed? If it began contracting, moving toward a big crunch instead of expanding forever? In 1985, Hawking and colleagues published a controversial paper suggesting that if the universe collapses, the thermodynamic arrow might reverse. Entropy would decrease during contraction. Time's arrow would flip. People would experience time running backward. They'd remember the future, not the past. This idea provoked intense debate. Many physicists disagreed, arguing that the thermodynamic arrow depends on local conditions, not cosmic expansion. Even in a contracting universe, entropy would continue increasing. Eggs would still break, never reassemble. Hawking later retracted the idea, admitting he'd made a mistake. The thermodynamic arrow doesn't reverse if the universe contracts. Time's direction is more subtle than he initially thought. But the question remains, why do all these arrows align? Why does time flow consistently in one direction? Perhaps the answer lies in the universe's quantum origins. Hawking's no-boundary proposal suggests the universe smoothly emerges from quantum geometry with no initial singularity. This provides naturally low entropy initial conditions. The smooth quantum state evolves into our expanding universe, entropy increasing from that low starting point. The thermodynamic arrow emerges from the universe's quantum birth. Another aspect of time troubles physicists. Time seems to pass. We feel it flowing, each moment giving way to the next. Yet the equations of physics, especially relativity, treat time as just another dimension, like space. Events are laid out along the time axis, all equally real. Past, present, and future coexist in space-time. This is the block universe view. The entire history of the cosmos exists statically, a four-dimensional structure with no genuine flow. Our perception of time passing is an illusion created by how our brains process information. Hawking held this view. He wrote, Time is just another direction in space. The distinction between past, present, and future is a feature of our consciousness, not of the universe itself. Relativity supports this. Simultaneity is relative. Events simultaneous for one observer occur at different times for another. There's no universal now slicing through space-time. Each observer has their own present moment, their own time axis. Yet this conflicts with our experience. We feel time passing. We sense the present moment as uniquely real, distinct from past and future. Reconciling physical theory with subjective experience remains an open question. By 1985, when Hawking published his controversial time arrow paper, he had lost his voice. The tracheotomy performed to save him from pneumonia left him unable to speak. He relied entirely on the speech synthesizer. Formulating thoughts took enormous effort, selecting words letter by letter, building sentences slowly, communicating at one word per minute. Despite this, he continued working on time's deepest mysteries. He thought about entropy, cosmology, quantum mechanics. He visualized time as a dimension, entropy as geometry, the universe's arrow as a consequence of boundary conditions. He communicated these thoughts painstakingly, contributing to debates, refining ideas, pushing physics forward. Time flows, entropy increases, the universe expands, and we exist briefly in this flow, conscious beings asking why, seeking to understand time's nature even as it carries us from birth to death. Hawking showed that time's arrow might be cosmological in origin, emerging from the universe's smooth quantum beginning. He showed that time is deeply connected to thermodynamics, to quantum mechanics, to space-time geometry. He showed that understanding time requires understanding everything, the whole universe from quantum foam to cosmic horizons. So as you drift, as time carries you gently towards sleep, reflect. You exist in time's flow, riding the arrow from past to future, experiencing moments that emerge and dissolve. The universe expands, entropy increases, time flows forward, and we are here, briefly, to wonder why. Now let us explore the deepest paradox Hawking encountered, the fate of information falling into black holes. If you're still with us in this quiet exploration of cosmic mysteries, you're part of something rare. Minds willing to drift through the deepest questions about existence, time, and reality itself. A quick subscribe helps others find this contemplative journey where physics meets philosophy. Now let's continue deeper into the paradox that haunted Hawking for decades, where information and reality collide at the edge of black holes. Chapter 6. The Information Paradox. Information is fundamental. In physics, information means the specification of a system's state, where particles are, how they're moving, what properties they have. Quantum mechanics says this information is conserved. It cannot be created or destroyed, only transformed. If you know a system's state now and the laws governing it, you can calculate its state at any past or future time. Information persists. Black holes challenge this principle. They seem to destroy information permanently, violating quantum mechanics' foundational rules. This is the black hole information paradox, one of theoretical physics' most profound unsolved problems. Here's the puzzle in detail. You throw a book into a black hole. The book contains information, every atom's position, every molecular bond, every letter on every page. This information encodes quantum states, specific configurations of particles and fields. When the book crosses the event horizon, it disappears from our view. We cannot observe it anymore, but the information still exists, encoded in the black hole's quantum state. Fine so far. The information is hidden but not destroyed. The black hole's state now includes everything about that book in principle. But black holes evaporate via Hawking radiation, over vast timescales, longer than the current age of the universe for stellar mass black holes but still finite. The black hole shrinks, losing mass through radiation. Eventually it evaporates completely. It vanishes. Hawking's calculation showed this radiation is thermal, random, featureless, containing no information about what fell in. It's like the radiation from a heated oven. You can measure temperature but cannot deduce what was cooked inside. The radiation carries energy but not information. So when the black hole finally evaporates, where is the information? The book's quantum state seems destroyed. The Hawking radiation contains no trace of it. Information has vanished from the universe. This violates quantum mechanics. It's not a minor technical problem. It's a fundamental contradiction. Quantum mechanics is our most successful physical theory, tested to extraordinary precision in countless experiments. It forbids information destruction. Yet Hawking's calculation, using well-established methods from quantum field theory and general relativity, suggests information is destroyed. Something must be wrong. But what? 4 possibilities have been debated for decades. Possibility 1. Hawking's calculation is incorrect. Perhaps the radiation is not purely thermal. Perhaps subtle correlations between emitted particles carry information, encoded in quantum entanglement too complex to detect easily. The information escapes gradually during evaporation, hidden in the radiation's quantum structure. This seems plausible, but proving it requires understanding quantum gravity, the theory that unifies quantum mechanics and general relativity. Hawking's calculation is semi-classical, treating spacetime classically while quantizing fields. A full quantum gravity treatment might reveal information escaping. Possibility 2. Information is destroyed, and quantum mechanics must be modified. Perhaps black holes represent situations where information can be lost, where the universe's history becomes non-deterministic, where pure quantum states can evolve into mixed states without environmental interactions. Hawking initially favoured this view. He argued that black holes introduce genuine randomness into physics beyond quantum mechanics' normal indeterminacy. This would be revolutionary, requiring major revisions to quantum theory's foundations. Most physicists rejected this. Quantum mechanics is too successful to abandon based on a theoretical puzzle. Possibility 3. Information remains inside the black hole until the very end, then escapes suddenly in the final evaporation burst. Perhaps the last stages of evaporation are dramatically different from earlier stages. When the black hole shrinks to near Planck scale, the smallest meaningful length, about 10 to the power of minus 35 meters, quantum gravity effects dominate, and the smooth horizon picture breaks down. Information might pour out in this final quantum explosion. This delays the problem rather than solving it. We still don't understand the mechanism for information release, and it requires physics at Planck scales, where we have no tested theory. Possibility 4. The horizon itself encodes information holographically. This is the holographic principle, one of the most radical ideas in modern physics. It proposes that all information contained in a region of space can be represented on that region's boundary. For black holes, information about everything inside is encoded on the event horizon's surface. This seems impossible. How can a 3-dimensional volume's contents be fully described by a 2-dimensional surface? Yet string theory and other approaches to quantum gravity suggest the holographic principle is correct. that our three-dimensional reality might be a projection from information encoded on a distant two-dimensional boundary. If the holographic principle applies to black holes, then information falling in gets encoded on the horizon. When the black hole evaporates, the horizon shrinks but continues carrying information. The Hawking radiation, though thermal from a semi-classical calculation, actually contains information in its quantum correlations. An observer who could measure every quantum property of every emitted particle, an impossible task practically, but possible in principle, could reconstruct what fell in. Hawking reversed his position on this paradox over his lifetime. Initially, he believed information is destroyed. In 1997, he made a bet with Kip Thorne and John Preskill. Hawking and Thorne bet that information is lost. Preskill bet it's conserved. In 2004, at a conference in Dublin, Hawking conceded. He presented calculations suggesting information escapes via subtle quantum correlations. The calculation wasn't complete. It relied on assumptions about quantum gravity, but Hawking found it convincing enough to admit he'd been wrong. He gave Preskill an encyclopedia, a baseball encyclopedia specifically. Hawking joked, "I gave John Preskill an encyclopedia of baseball, from which information can be retrieved at will." Preskill accepted graciously, though he later commented the paradox isn't fully resolved. The information paradox remains open. We lack the necessary theory, quantum gravity, to solve it definitively. String theory offers hints, suggesting the holographic principle and subtle quantum correlations preserve information. Loop quantum gravity and other approaches propose different mechanisms, but we don't have experimental tests. We cannot create black holes in laboratories, observe their evaporation, measure their radiation's quantum properties. Yet the paradox drives progress. It forced physicists to think deeply about information, entropy, and quantum gravity. It revealed connections between black hole thermodynamics and quantum information theory. It led to the holographic principle, now a central idea in theoretical physics. Hawking spent decades wrestling with this puzzle. By the 1990s, he communicated only through the speech synthesizer, 1 word per minute. Formulating complex arguments about quantum information, black hole horizons, and thermodynamics took extraordinary effort. Yet he persisted. He once described his approach: think visually, geometrically. Picture the horizon, imagine quantum fields, visualize particle creation. Don't get lost in equations, see the physics. This visual approach helped him tackle the information paradox. He imagined information encoded on the horizon, stretching and evolving as the black hole evaporates. He thought about quantum entanglement linking interior and exterior regions. He visualized space-time foam at Planck scales, quantum fluctuations where smooth geometry breaks down. And through these visualizations, he contributed to our understanding, even without a final solution. He showed where the problem lies, what principles conflict, what questions must be answered. He transformed the paradox from a vague worry into a precise technical challenge. So as you rest, as your thoughts settle, contemplate. Information seems indestructible, encoded in reality's quantum structure. Yet black holes challenge this. They hide information behind horizons, emit radiation that seems random. The tension between quantum mechanics and gravity becomes acute, forcing us toward a deeper theory. Hawking illuminated this tension. Now let us see how he shared these ideas with the world. Chapter 7. A Brief History of Time. In 1988, Stephen Hawking published A Brief History of Time, From the Big Bang to Black Holes. It became one of the most famous science books ever written. It sold more than 10 million copies worldwide, stayed on bestseller lists for years, and transformed Hawking from respected physicist into global celebrity. The book attempted something ambitious: explain cosmology, relativity, quantum mechanics, and black holes to general readers with no scientific background. Hawking wanted to share the universe's wonders, make cutting-edge physics accessible, show that the deepest questions about existence are comprehensible. He succeeded beyond anyone's expectations. The book's success surprised even Hawking. Why did it resonate so powerfully? Part of the answer is his clear, engaging writing. He avoided jargon, used vivid analogies, explained complex ideas step by step. He addressed grand questions. Where did the universe come from? Does time have a beginning? What is the nature of reality? But part of the success was Hawking himself. By 1988, he was internationally recognized, not just for his science, but for his remarkable life story. A man given 2 years to live at age 21, now 46 and still working. A brilliant physicist trapped in a failing body, communicating through a computer, defying every prediction. The book's author became part of its appeal. Writing the book was an immense challenge. Hawking had lost his voice 3 years earlier. He composed every sentence using the speech synthesizer, selecting words letter by letter through muscle twitches. A graduate student, Brian Witt, helped organize material and transcribe Hawking's synthesized speech. Editor Peter Guzzardi at Bantam Books shaped the manuscript, pushing Hawking to simplify, clarify, make the text accessible. Hawking famously said his publisher warned that each equation in the book would halve sales, so he included only one: Einstein's E equals mc squared. Everything else, relativity, quantum mechanics, black hole thermodynamics, was explained in words, diagrams, analogies. No mathematics visible, though rigorous physics concepts throughout. The book's structure mirrored Hawking's intellectual journey. It began with the universe's origins, discussing the Big Bang, expansion, and time's beginning. It moved to relativity, explaining space-time curvature, gravity, and Einstein's revolutionary ideas. Then black holes, their formation, properties, and the paradoxes they create. Finally, quantum cosmology, the no-boundary proposal, and questions about God's role in creation. Hawking's writing was personal. He discussed his own work openly, describing his doctoral research, his collaborations, his debates with colleagues. He admitted uncertainties, acknowledged when ideas were speculative. He conveyed the excitement of discovery, the joy of understanding something new about the universe. He also addressed philosophical implications. If the universe has no boundary in time, no initial moment requiring creation, does God have a role? Hawking wrote, "If the universe is really completely self-contained, having no boundary or edge, it would have neither beginning nor end. It would simply be. What place then for a creator?" This provoked discussion, some controversy. Religious leaders debated Hawking's views. Some saw his science as threatening faith. Others appreciated his honest engagement with ultimate questions, arguing that understanding how the universe works doesn't diminish wonder or spirituality. Hawking himself was not hostile to religion. He respected people's beliefs, though he didn't share them. He sought natural explanations for the universe's existence, but acknowledged science answers how rather than why. Why does the universe exist? Why these laws of physics? Why anything at all? Science cannot answer these questions. They transcend empirical investigation. A brief history of time made Hawking famous worldwide. He appeared on television shows, met celebrities, became a cultural icon. He guest starred on The Simpsons, playing himself, making jokes through his synthesizer. He appeared on Star Trek: The Next Generation in a poker game with Einstein, Newton, and Data. He enjoyed this celebrity, the opportunity to communicate science broadly, to inspire curiosity. His fame had drawbacks: constant attention, requests for interviews, public appearances. These took time from research. He struggled to balance scientific work with public engagement. But he valued outreach. He believed scientists should communicate, make their discoveries accessible, inspire the next generation. The book's success led to documentaries, interviews, lectures. Hawking became science's public face, the person non-scientists associated with cosmology and black holes, the voice, literally given his synthesizer, of modern physics. When people thought of physicists, they thought of Hawking. This visibility brought opportunities. Funding for his research improved. Cambridge provided resources, assistance, equipment. He travelled widely, lecturing at universities and conferences despite physical limitations. A team of caregivers accompanied him, managing his wheelchair, his computer, his medical needs. But the fame also created distance. Colleagues sometimes felt uncomfortable, unsure how to interact. Was he Stephen the scientist or Hawking the celebrity? Students hesitated to approach. The speech synthesizer added barriers. Conversations required patience, as Hawking formed responses slowly. Yet he continued. Through the 1990s and 2000s, Hawking published more books: Black Holes and Baby Universes, The Universe in a Nutshell, The Grand Design, and each aimed to share cosmology's wonders, explain recent developments, address big questions. None matched A Brief History of Time's success, but all sold well, reaching audiences hungry for insight into the universe's nature. Hawking also wrote a children's book with his daughter Lucy, George's Secret Key to the Universe, introducing young readers to physics through adventure stories. He wanted to inspire children's curiosity, show them science is exciting, accessible, fun. By the late 1990s, Hawking's personal life had changed dramatically. His marriage to Jane ended in 1991 after 26 years. The strain of caregiving, combined with diverging interests and worldviews, had taken a toll. Jane later wrote movingly about those years: the love, the struggle, the impossible situation of caring for a brilliant man whose body required constant, exhausting attention. Hawking married Elaine Mason, one of his nurses, in 1995. This marriage also ended in divorce in 2006. His relationships were complex, shaped by his dependence on caregivers, the blurred lines between personal and professional support, the immense challenges of intimacy when physical connection is nearly impossible. Through all of this, fame, personal upheaval, worsening disability, he continued working. He thought about black holes, quantum gravity, cosmology. He mentored students, collaborated with colleagues worldwide, contributed to physics despite communicating at 1 word per minute. A Brief History of Time remains his most enduring legacy for the general public. It showed that science's deepest ideas can be shared, that curiosity about the universe transcends academic boundaries, that understanding reality is a human endeavour, not just for specialists but for anyone willing to think, question, wonder. So as your mind drifts, as you settle into rest, remember the universe. Hawking described, expanding, governed by gravity and quantum mechanics, filled with black holes and radiation, is the universe you inhabit. His book brought cosmology to millions. His life demonstrated that physical limitations cannot constrain human thought. Now let us explore how he lived with ALS, conducting physics despite everything. Chapter 8. Living with ALS, physics despite everything. Stephen Hawking lived with amyotrophic lateral sclerosis for 55 years, longer than anyone expected, far exceeding medical predictions. His experience with ALS shaped his life, his science, and his outlook on existence. ALS is brutal. It attacks motor neurons, nerve cells controlling voluntary muscles. As these neurons die, muscles atrophy. Movement becomes difficult, then impossible. Speech slurs, swallowing becomes dangerous. Breathing requires assistance. Yet the mind remains intact. Consciousness, memory, reasoning, all unaffected. You're fully aware, fully present, trapped in a body that no longer responds. Most ALS patients die within 3 to 5 years of diagnosis. Hawking was diagnosed at 21, given 2 years. He lived to 76. Why? We don't entirely know. His disease progressed unusually slowly for reasons still unclear. Perhaps genetic factors. Perhaps the specific form of ALS he had. Perhaps luck. Whatever the reason, this slow progression gave him decades to work. But those decades came with immense challenges. Daily life required constant assistance. He needed help dressing, eating, moving. Privacy became impossible. Caregivers were always present, necessary, appreciated, but still a barrier to independence. Yet Hawking maintained humour. His speeches, written laboriously through the synthesizer, often included jokes. He appeared on comedy shows, made fun of himself, refused to let his condition define his public persona. When interviewed, he discussed physics, not disability. He wanted to be known for his mind, not his wheelchair. His method of working adapted to his limitations. Early in his career, before ALS fully progressed, he could write equations, attend seminars, participate normally. As movement became difficult, he shifted to mental calculation. He visualized mathematics geometrically, manipulated equations mentally, developed an intuitive understanding of physics that didn't require notation. This mental approach had advantages. He saw relationships others missed. While colleagues got lost in algebraic details, Hawking grasped underlying geometry. He thought in pictures, curved surfaces, particle trajectories, field configurations. This visual thinking led to insights about black holes, cosmology, quantum fields in curved space-time. Graduate students and collaborators learned to work with him. He'd pose a problem, think for days or weeks, then announce results. Colleagues would work backward, filling in mathematical details, verifying his geometric intuitions with formal calculations. Often, Hawking was right. His visualizations captured physical truth that rigorous mathematics confirmed, but the process was slow. A paper that might take another physicist weeks to write took Hawking months. Every sentence required selecting words letter by letter. Every equation had to be described verbally, then translated by colleagues into mathematical notation. Collaboration was essential but complicated. Despite these challenges, Hawking's productivity remained impressive. He published dozens of papers, contributed to multiple fields, mentored students, organized conferences. His office at Cambridge became a gathering place for cosmologists and quantum gravity researchers from around the world. Travel was difficult but managed. Hawking visited universities and research centres internationally. His wheelchair, computer equipment, and medical supplies required careful coordination. Caregivers accompanied him everywhere. Yet he lectured widely, enjoyed engaging with new ideas, meeting colleagues face to face. He attended conferences actively. During talks, he'd signal questions or comments. His graduate students or assistants would help formulate the response, then read it to the audience. This process interrupted presentations, but people accepted it gladly. Hawking's contributions were worth the inconvenience. Personal life was complicated. His first marriage to Jane lasted 26 years, producing 3 children. Jane's memoir, Traveling to Infinity, later adapted into the film The Theory of Everything, described their relationship with honesty and love. She depicted the early romance, the shock of diagnosis, the decision to marry despite knowing what lay ahead. She also described the immense burden, caring for Stephen while raising children, managing a household, maintaining her own career and identity. It was overwhelming. Support from family, friends, and eventually professional caregivers made it possible. But the strain was immense, unsustainable indefinitely. After their divorce, Jane wrote, "I felt that I had been through the mill. I'd given everything, done my best, and it was not enough." Yet she also expressed pride in what they accomplished together, gratitude for the years they shared, appreciation for Stephen's brilliance and determination. Hawking's second marriage to his nurse Elaine Mason was intense and complex. It ended in divorce in 2006. Friends described that period as turbulent. Allegations of mistreatment surfaced, though Hawking denied them and no charges were filed. The truth remains private, known only to those directly involved. Through these personal upheavals, Hawking kept working. Physics was his constant, something reliable when relationships, health, and circumstances changed. Equations don't judge. Space-time geometry doesn't require emotional labor. The universe remains beautiful regardless of human difficulties. Hawking also found meaning in humor. He enjoyed clever wordplay, appreciated good jokes, loved British comedy. He appeared on shows like Red Nose Day, Little Britain, and The Big Bang Theory. He let writers use his synthesizer's voice for comic effect, poking fun at his own image. One famous joke: at a university event, someone asked Hawking if his computer could simulate human intelligence. His synthesizer replied, "Why would I want to simulate human intelligence when I have the real thing?" The audience laughed. Hawking's cursor blinked. "I was talking about you." This humour reflected deeper resilience. ALS took his mobility, his voice, almost everything physical. But it couldn't touch his mind, his curiosity, his determination to understand reality. He transformed limitation into strength, using his constrained perspective to see physics differently. He once said, "My disability has not been a serious handicap in my scientific work. In fact, it may have helped in some ways." How? By forcing mental visualization, by eliminating distractions, by making every thought count. Unable to casually jot equations, he thought deeply before committing ideas to painstaking communication. His advice to others facing challenges: look up at the stars, not down at your feet. Be curious. However difficult life may seem, there is always something you can do and succeed at. This became his unofficial motto, a message of hope grounded in his own experience. Hawking's final years were medically complex. By the 2000s and 10s, he required round-the-clock care. Breathing difficulties, infections, pneumonia, each threatened his life. Yet he continued. He travelled to conferences, gave lectures, worked on papers until weeks before his death. He died peacefully at home in Cambridge on March 14th, 2018, Pi Day, and coincidentally Einstein's birthday. His ashes were later interred in Westminster Abbey between Isaac Newton and Charles Darwin, fitting company for a man who transformed our understanding of the universe. His legacy extends beyond physics. he demonstrated that human value transcends physical capability, that minds can achieve greatness regardless of bodily limitations, that curiosity and determination can overcome nearly any obstacle. He inspired millions, not just physicists, but anyone facing challenges, seeking meaning, wondering about existence. So as you rest, as you prepare for sleep, reflect on this. Hawking spent decades unable to move, yet travelled through black holes in his mind. He communicated at 1 word per minute, yet shared the universe's deepest secrets. He faced terminal illness at 21, yet lived 55 more years doing brilliant physics. The human spirit, when coupled with curiosity and determination, transcends any limitation. Now let us ask, are there other universes beyond our own? Chapter 9. The Multiverse. Are we one of many? Our universe seems finely tuned. The laws of physics, the values of fundamental constants, these appear precisely calibrated for complexity, structure, life. Change any constant slightly, and the universe becomes sterile, unable to produce stars, atoms, chemistry, biology. Consider gravity's strength. If gravity was slightly stronger, stars would burn too fast, exhausting fuel before life could evolve. Slightly weaker and stars wouldn't ignite at all. No nuclear fusion, no heavy elements, no planets. The actual value sits in a narrow range permitting stable, long-lived stars. Or consider the electromagnetic force. If it were stronger, atoms wouldn't bond into molecules. Chemistry would be impossible. Weaker, and electrons wouldn't stay bound to nuclei. Matter would disintegrate. Again, a narrow range permits complexity, or the cosmological constant, dark energy's strength. Current observations suggest it's positive but tiny, causing gentle cosmic acceleration. If it were much larger, the universe would have expanded too rapidly for galaxies to form. If negative, the universe would have collapsed long ago. The actual value is extraordinarily small yet non-zero, fine-tuned to about 1 part in 10 to the power of 120. Why? Why do these constants have the specific values they have? Why is the universe habitable rather than sterile? One answer: pure chance. The constants could have been anything, and they happened to permit life. No deeper explanation needed. We observe these values because if they were different, we wouldn't exist to observe them. This is the weak anthropic principle. Observations must be compatible with the observer's existence. But this feels unsatisfying. The fine-tuning seems too precise, too specific to dismiss as accident. It's like shuffling a deck of cards and drawing a royal flush 10 times in a row. Possible? Yes. Requiring explanation? Most would say yes. Another answer: design. Someone or something set the constants deliberately, creating a universe capable of supporting life. This appeals to theistic worldviews, suggesting divine intention behind cosmic architecture. But it's not scientific. It doesn't generate testable predictions, doesn't explain the mechanism, shifts the mystery rather than resolving it. A third answer, explored seriously by physicists: the multiverse. Perhaps our universe is one among many, countless universes with different laws, different constants, different properties. In most, complexity is impossible. But in rare universes like ours, conditions permit stars, planets, life. We find ourselves in a habitable universe not because it's special, but because we couldn't exist in the others. This is the strong anthropic principle. The universe must have properties compatible with life because only in such universes do observers exist to notice. Our observations are selection biased. We necessarily observe a habitable universe, regardless of how rare such universes might be. Stephen Hawking engaged with multiverse ideas throughout his career. He was initially skeptical, finding them untestable and philosophically troubling. Science explains observations through testable theories. Multiverse hypotheses seem to avoid explanation by postulating unobservable domains beyond empirical reach, but he recognized their theoretical appeal. In cosmology, several mechanisms could generate multiverses. One is eternal inflation. Recall that cosmic inflation, the exponential expansion in the universe's first fraction of a second, may not be a one-time event. In eternal inflation models, space continues inflating in most regions. Occasionally, inflation stops in a local region, creating a bubble universe like ours. But elsewhere, inflation continues, producing more bubbles. The result: countless bubble universes, each with potentially different physics. Another mechanism comes from string theory. String theory attempts to unify all forces, including gravity, by describing particles as vibrating strings in higher dimensional space. The theory requires extra dimensions beyond the familiar 3 of space and 1 of time, perhaps 6 or 7 additional dimensions curled up at scales too small to observe. These extra dimensions can be arranged in many ways, potentially 10 to the power of 500 different configurations, called the string theory landscape. Each configuration corresponds to different low-energy physics, different particle masses, different force strengths, different constants. If all these configurations are realized somewhere, we have a vast multiverse of universes with varying properties. Hawking found this landscape troubling. If string theory permits 10 to the power of 500 different universes, it loses predictive power. We cannot calculate which universe we inhabit or predict specific observations. The theory becomes descriptive rather than predictive. It accommodates any observation by postulating some universe in the landscape matches reality. Yet Hawking also recognized the anthropic principle's utility. In 2006, he and colleague Thomas Hertog proposed a top-down cosmology approach. Instead of asking how did the universe begin and evolve to its current state, they suggested asking, given our observations, what initial conditions and histories are compatible? This reverses the usual reasoning. Normally, we assume a single history, one timeline from Big Bang to present. Top-down cosmology suggests multiple histories coexist quantum mechanically, and observations select among them. The universe's state now constrains the probabilities of different pasts. This approach incorporates multiverse ideas and anthropic reasoning. If many histories are possible, we observe the one compatible with our existence. Other histories, those leading to sterile universes, remain possible but unobserved because no observers exist there. Critics argue this abandons explanation for tautology. We observe what we observe because we observe it, but Hawking and Hertog argued it's pragmatic. If we cannot observe other universes directly, we must infer cosmic properties from our observations alone. Top-down cosmology makes this precise. The multiverse remains controversial. Some physicists embrace it as the only way to explain fine-tuning without invoking design. Others reject it as unscientific speculation, philosophy dressed as physics. Experiments cannot test multiverse hypotheses directly. We cannot observe other universes, visit them, measure their properties, yet indirect tests might be possible. Cosmic inflation predicts specific patterns in the cosmic microwave background. Observing these patterns test inflation, lending credence to eternal inflation scenarios. Gravitational waves from inflation, if detected, would provide further evidence. The multiverse hypothesis becomes more plausible if mechanisms generating it are confirmed. Hawking's position evolved. By the end of his life, he accepted the multiverse's possibility, seeing it as a natural consequence of quantum cosmology and inflation. He didn't claim certainty, only that multiverse scenarios deserve serious consideration, that they address real puzzles about fine-tuning and cosmic origins. He also emphasized humility. We don't know if other universes exist. We don't know if the string landscape is real. We don't know if inflation is eternal. These are open questions requiring more theory, more observations, more thought. But asking the questions drives progress. Multiverse hypotheses force us to think carefully about what makes theories scientific, what counts as evidence, how we infer unobservable reality from observable consequences. They push physics toward deeper understanding of why anything exists at all. So as your thoughts settle, as you drift towards sleep, contemplate. You may inhabit one universe among countless others, a rare bubble where constants permit complexity, where stars shine and minds ponder existence. Or perhaps this universe is alone, its properties brute facts requiring no explanation beyond quantum emergence. Either way, you are here, conscious, curious, part of a cosmos vast beyond imagination. Now, let us ask the ultimate question Hawking confronted. Chapter 10. The ultimate question. Why is there something? Why does the universe exist? Why is there something rather than nothing? This is philosophy's deepest question, confronting the mystery of existence itself. Most questions science addresses assume existence. How do stars form? Why do galaxies cluster? What creates black holes? These presuppose a universe containing stars, galaxies, black holes. But step back further. Why does any universe exist? Why are there laws of physics at all? Why does reality contain anything? For millennia, this question led to God. Only a necessary being, something existing by its own nature, requiring no external cause, could explain contingent existence. The universe exists because God created it. God exists necessarily needing no creator. The chain of causation terminates in the divine. Stephen Hawking approached this question scientifically. Can physics explain existence without invoking supernatural creation? Can the universe arise from nothing through natural processes alone? His answer, possibly yes. Quantum mechanics permits creation from nothing. The laws of physics, especially quantum field theory, allow particles to appear spontaneously from the vacuum. Virtual particles pop into existence constantly. Usually they annihilate almost immediately, but occasionally fluctuations persist, become real, contribute to observable phenomena. If particles can appear from nothing, why not space and time? Why not an entire universe? Hawking proposed that quantum processes could generate the universe. In his no-boundary proposal, developed with James Hartley, the universe emerges from quantum geometry without a singular beginning. Time itself becomes space-like near the origin, smoothly transitioning from non-existence to existence with no boundary, no moment requiring creation. Imagine asking, what came before the Big Bang? In Hawking's picture, this question is meaningless. Time begins with the Big Bang, or rather, time emerges smoothly from quantum geometry. There is no before, because time itself doesn't extend past the origin. Asking what came before is like asking what lies south of the South Pole. The question assumes a structure that doesn't exist. This removes the need for a first cause. If the universe has no beginning, no initial moment, then existence requires no external explanation. The cosmos is self-contained, arising through quantum processes governed by physical law. But this raises a deeper question. Why these laws? Why do the laws of physics permit quantum fluctuations Virtual particles, space-time emergence. Why not different laws or no laws at all? Hawking addressed this in his final book, The Grand Design, written with Leonard Mlodinow. They argued that the laws of physics are not arbitrary but may be logically necessary. M-theory, a version of string theory unifying different string theories, might be the only consistent mathematical framework allowing a self-contained universe. If so, the laws of physics exist necessarily, just as mathematical truths exist necessarily. 2 + 2 = 4, not because someone decided it, but because it's logically required. Similarly, perhaps the laws governing quantum mechanics and gravity are logically required, the only consistent way to describe reality. If this is true, Hawking argued, the universe creates itself. Quantum processes operating under necessary physical laws generate space-time, matter, energy, everything. God becomes unnecessary. As Hawking wrote, because there is a law like gravity, the universe can and will create itself from nothing. Spontaneous creation is the reason there is something rather than nothing, why the universe exists, why we exist. This is bold. It claims to answer philosophy's ultimate question scientifically, but it's also controversial. Critics point out that nothing in quantum mechanics isn't truly nothing. It's the quantum vacuum, a state governed by physical laws containing fields and potential energy. True nothing would have no laws, no fields, no quantum mechanics. Spontaneous creation requires something. The laws and framework of quantum field theory. Hawking acknowledged this. His nothing wasn't absolute non-existence but the quantum vacuum state. Whether this counts as a genuine explanation for existence depends on whether physical laws themselves require explanation. Some argue yes, laws are contingent, could have been different, require external justification. Others argue no, laws may be necessary, the only logically consistent framework, requiring no further explanation than mathematical theorems do. Hawking leaned toward the latter view. He believed physics can explain existence completely, that the universe is comprehensible through reason alone, that no supernatural intervention is needed. This is scientific naturalism, the view that reality is governed entirely by natural law, discoverable through empirical investigation. But Hawking admitted uncertainty. We lack a complete theory of quantum gravity. M-theory is speculative, untested experimentally. The no-boundary proposal is elegant but unproven. These ideas point toward answers, but the full story remains unknown. He also acknowledged existential wonder. Even if physics explains how the universe exists, questions remain. Why is there anything rather than nothing? Why do we find ourselves conscious, able to ask questions, ponder existence? These questions touch meaning, purpose, consciousness, domains where science offers insights but not complete answers. Near the end of his life, Hawking reflected on the ultimate question. In an interview he said, "I regard the brain as a computer which will stop working when its components fail. There is no heaven or afterlife for broken down computers. That is a fairy story for people afraid of the dark." This sounds bleak, but he also emphasized wonder, understanding that we are temporary, that consciousness emerges from physical processes, that the universe requires no cosmic purpose. This doesn't diminish life's value. It amplifies it. We are here, briefly. We can think, feel, discover, love. We are the universe becoming aware of itself. Hawking found profound meaning in this. Not cosmic meaning imposed from outside, but meaning we create through curiosity, compassion, understanding. We exist in a vast ancient cosmos governed by comprehensible laws. That we can understand anything at all is extraordinary. His final message to humanity: be curious, ask questions, seek understanding, look outward at the stars and inward at the mysteries of mind. Don't accept ignorance. Don't surrender to superstition. Use reason, evidence, and imagination to explore reality. He also emphasized responsibility. Understanding the universe doesn't automatically make us wise. Science grants power to cure disease or create weapons, to explore space or destroy ecosystems. How we use that power depends on choices, values, wisdom. Hawking worried about humanity's future. Climate change, nuclear weapons, artificial intelligence, these pose existential risks. He advocated for addressing them seriously, applying scientific understanding to ensure our survival. The universe is indifferent to humanity. If we destroy ourselves, the cosmos continues. Our existence is our responsibility. Yet he remained hopeful. Humans are curious, creative, capable of extraordinary achievements. We've gone from caves to spacecraft, from mythology to quantum mechanics, from ignorance to understanding. We can continue this journey, exploring space, unraveling reality's deepest mysteries, becoming a civilization that endures. So as your mind drifts towards sleep, as consciousness fades gently into rest, hold this thought: you exist. Against overwhelming odds, in a universe vast and ancient, you are here, aware, thinking, part of the cosmos examining itself. Stephen Hawking showed that existence is comprehensible, that questions have answers, that human minds can grasp the universe's deepest secrets. His life demonstrated that limitations need not constrain thought, that curiosity transcends any obstacle, that the human spirit reaches beyond the stars. Rest now and dream of the mysteries still waiting to be understood. We have journeyed through Stephen Hawking's universe, from the Big Bang's quantum origins to black holes' event horizons, from time's arrow to the multiverse's possibilities, from information paradoxes to existence itself. We've seen how a man trapped in a failing body soared through space-time, explored cosmic mysteries, and transformed our understanding of reality. Hawking's legacy is profound. He showed that the universe has a beginning, but may be boundless. He revealed that black holes glow with radiation, connecting gravity to quantum mechanics and thermodynamics. He asked whether time is fundamental or emergent, whether information is destroyed or preserved, whether our universe is alone or one among many. He also demonstrated that physical limitations cannot constrain human thought. Diagnosed with terminal illness at 21, Hawking lived 55 more years, conducting brilliant physics despite communicating at 1 word per minute. His mind transcended his body's constraints, reaching across billions of light years and back to time's beginning. His message remains vital. Look up at the stars, not down at your feet. Be curious, ask questions, seek understanding. The universe is vast, mysterious, and beautiful, and it is comprehensible. Through reason, observation, and mathematics, we can understand reality's deepest truths. This is episode 3 of Through Their Eyes, Science's Greatest Minds. We've explored the universe through Einstein's revolutionary vision of space-time, Feynman's playful approach to electricity and quantum fields, and now Hawking's contemplation of cosmic origins and black holes. Next, we'll continue this journey through other brilliant minds who transformed our understanding of nature. Subscribe to Sleep Entangled to join us as we explore light through Maxwell's eyes, atoms through Rutherford's experiments, and evolution through Darwin's revolutionary insights. Until then, rest peacefully. You inhabit a universe born from quantum fluctuations, expanding through cosmic time, containing black holes that evaporate and stars that shine. You are part of this cosmos, conscious matter pondering existence, brief moments of awareness in an ancient universe. This is sleep entangled, where science and wonder merge into quiet journeys. Thank you for exploring the universe through Hawking's eyes. Good night, and may curiosity guide your dreams.